In the last few weeks, we explored the notion of differentiability in great detail. Just like in the real analysis setting, the notion of differentiability is tied down, the notion of complex differentiability is also tied down together with the notion of integration. And among the notions of integration, we will be most interested in integration along curves, or rather line integrals. We will plunge into that in the next few weeks, but in this lecture, let's review and recall the notion of curve and the various properties of curves. Let's begin this lecture by recalling what a curve is. So, definition of a curve. So, a continuous parameterized curve which we will often just refer to as a curve. This is a continuous map. We have already seen this while we went through the review of various topological notions on the complex plane. So this is a continuous map gamma from a closed interval AB in real line into the complex plane. If the point A is equal to B, then we say that the curve is trivial. Let me just note that if A is equal to B, then the curve is trivial. So, I will not be focusing on just curves from 0, 1. We will come to that, the domain etc. will be the domain of definition of the curve will be of interest. We will come to that when we look at reparameterization and such stuff. Right now, AB is an arbitrary interval on the real line, and a continuous parameterized curve, which we will just call as a curve from now, is a continuous map from AB into C. The curve is said to be trivial if A is equal to B, and if it is not equal, then it is a non-trivial curve. The point gamma of A, where the curve begins, is called the initial point, and the point gamma of B, where the curve ends, is called the terminal point of gamma. It's called the initial point. So notice that gamma of A is the image. It's not A that we are looking at. The image of A under gamma is called the initial point of gamma, and gamma of B is called the terminal point, right? Now it can happen that even though A is not equal to B, gamma of A is equal to gamma of B, and if that happens, we say that our curve gamma is a closed curve. Gamma is said to be a closed curve if gamma of A is equal to gamma of B. So notice that the word closed here is not the topological notion of closed we are familiar with, because gamma is a continuous map from a compact set AB into C, and therefore the image of gamma is always going to be a closed set. Here, when we say that gamma is a closed curve, we demand that the initial point and the terminal point of gamma coincide. That's when we say that gamma is a closed curve. Gamma is said to be simple if it is injective in the interior of AB. We say that gamma is a simple curve if gamma of t is not equal to gamma of t prime of t equal to a, t prime equal to b, or t equal to b, t prime equal to a. Okay, when the endpoints are not being considered, then in the interior gamma is injective. If that happens, then we say that gamma is a simple curve. Now, oftentimes gamma is, even though the map gamma is what we study, it is the image in the complex plane that gives us the geometric idea of what the curve is. So the image gamma of AB of gamma is called the image of the curve. Okay, so we have given quite a few definitions. Let's look at a few examples. The first example is a straight line from a point z1 to z2. So let z1 and z2 be 2 points in the complex plane. Gamma z1 to z2 of t, this is defined to be 1 minus t times z1 plus t times z2. What is that? At t equal to 0, this is z1, at t equal to 1, it is z2. So this is the straight line path which we are familiar with. So this curve is one of the first examples. Second example would be the following. The unit circle or a circle of radius r around a point z0. Let's capture that. Now that we have the polar decomposition in our repertoire, let's use it. Define gamma of t to be equal to, oh yes, so here t is in the interval 0, 1. So we are defining the curve in the domain of definition close 0, 1. In the case of the circle, let's define it to be z0 plus r, maybe I should use the variable theta, r e to the power I theta, that theta now belongs to 0 to 2 pi. So here what is the initial point in the first case? The initial point is z1, the terminal point is z2, and it is indeed a simple curve. It's not a closed curve if z1 is not equal to z2. But if z1 is equal to z2 in the first case, I am still in this example, if z1 is equal to z2, then what happens is gamma z1 to z2 will just turn out to be a singleton, namely the point z1 or z2. I would like to stress that even in that case, our curve gamma is not a trivial curve. It's a non-trivial curve which is closed but not simple. That's how the first curve is going to transform into when z1 is equal to z2. But when z1 is not equal to z2, it's a non-trivial curve which is a simple curve which is not a closed curve. Okay, let's get to the second example which we had already started, namely that of circle of radius r around z0. So here you should note that the initial point is z0 plus r and the terminal point is also z0 plus r. So this is indeed a closed curve and it is also a simple curve. So let me just state it here and leave it at that. Gamma is a simple closed curve. So when I say curve, it's continuous parameterized curve. Right, what will be the image? The image is just going to be the circle of radius r around z0. Let's now define gamma 1 of theta to be equal to, again similarly, z0 plus r e to the power 2 pi I theta, but now theta is defined from 0 to 1. So if you notice, the properties of gamma 1 is very similar to that of gamma. Its initial and terminal point are the same as that of gamma. It's a simple closed curve whose image is also the same. But then we still treat these as different curves because the first curve is defined on 0, 2 pi and the second curve is defined on 0, 1. How about gamma 2 of theta defined by z0 plus r e to the power 2 I theta, where theta is again in 0 to 2 pi. If you notice, this is again very similar to the first curve. However, there is a difference. The first two examples, this one and this one, were not just closed curves, they were simple closed curves. This, however, is not a simple closed curve because for any point on the circle, there are two p images. It's not injective in the interior in particular. So, yeah, so we would like to somehow identify these two curves, the first two curves, gamma and gamma 1, and the right notion to look at for the purpose of identifying these two is what is called as a reparameterization, a continuous reparameterization. So let's define what a continuous reparameterization of a curve gamma 1 is. We say that a curve gamma 2 from say A to B2 into C is a continuous reparameterization of gamma 1, which is from say A1 B1 into C, if there exists a homeomorphism. A homeomorphism is just a bijective continuous map whose inverse is also continuous. So phi is now a map from A1 B1 to A2 B2. So in particular, this is going to be a continuous map which is a bijection from A1 B1 to A2 B2 such that its inverse is also continuous, such that the endpoints are preserved. Phi of A1 is equal to A2 and phi of B1 is equal to B2, and such that gamma 2 of phi of t is equal to gamma 1 of t for all t in A1 B1. So if you notice, the first two examples here are obtained by a continuous reparameterization. You just map 0 1 to 2 pi by the map t going to 2 pi t, and if you look at that map as phi, then gamma 1 is going to be a continuous reparameterization of the curve gamma. Notice that the direction or the orientation is being preserved. So for example, gamma z2 to z1 is not reparameterization of gamma z1 to z2. Why? Because if z1 and z2 are distinct, the initial point of this curve is z2 and the initial point of this curve is z1. And by the definition of reparameterization that we have defined here, if you notice, this condition that phi of A1 is equal to A2 and phi of B1 is equal to B2 forces the curves, reparameterized curves, to have the same initial point and the terminal point. Also, this condition forces that the image is the same. So this is certainly not a reparameterization, because even though the image is the same, the initial and the end point are not the same. The notion of continuous reparameterization is an equivalence relation. That's the most important aspect here. Let me just note that continuous reparameterization is an equivalence relation. Let me elaborate on this. If gamma 1 is obtained, or if gamma 2 is obtained by reparameterization of gamma 1, then we say that gamma 1 is equivalent to gamma 2. And this statement, let me just leave it as an exercise for you. It just tells us that this relation that we just defined is an equivalence relation. It's actually quite straightforward to check. A curve gamma is obtained by a continuous reparameterization of itself by considering the identity maps which are related to itself. And if you look at phi inverse, then if gamma 2 is obtained by a continuous reparameterization of gamma 1 through phi, then phi inverse will give us the relevant parameterization to obtain gamma 1 as a reparameterization of gamma 2. And for transitivity, if you look at phi 1 and phi 2 as being two maps from say A1 B1 to A2 B2 and then A2 B2 to A3 B3, then you compose it, you will get a map from A1 B1 to A3 B3, and that will serve as the relevant map for the parameterization of gamma 3 in terms of gamma 1. And gamma 1, gamma 2, gamma 3 were picked according to the indices. Alright, so I'll leave this as an exercise for you to check that continuous reparameterization is an equivalence relation. So most often we will be interested only in studying most of the notions up to this equivalence relation. So, we will always mention whether it is being done up to continuous reparameterization or not. If the situation is not clear, we will not even bother doing that. Okay, let us get back to the example of the non-example rather of a continuous reparameterization which was given above. Gamma Z2 to Z1 is not obtained as a continuous reparameterization of Z1 to Z2, the straight lines, because the initial and the terminal point don't match. However, this is exactly what we refer to as the reversal of a curve gamma. Let me define that for you. We say that a curve minus gamma is a reversal of gamma if minus gamma of t of a curve gamma, let me just explicitly mention where it is from, of a curve gamma from AB to C, if minus gamma is defined from minus B minus A into C and minus gamma of t is defined to be gamma of minus t. And the first thing to note here would be that example would be to check that gamma Z2 to Z1, the straight line joining Z2 to Z1, that's not a reversal of Z1 to Z2, but it is going to be equivalent to the reversal of gamma Z1 to Z2. So, it is a good exercise for you to understand all these things, all these notions. It might be a good idea to explicitly sit down and construct the reparameterization from this curve to this curve. Notice that minus gamma from Z1 to Z2 is indeed a map from Z2 to Z1. Gamma Z2 to Z1 is also a map from Z2 to Z1. They are not the same curves to begin with, because this is going to be defined from minus 1 comma 0 and this is going to be defined on 0 comma 1. So, there are two different domains of definition that are involved, but I urge you to sit down and get hold of the right homeomorphism from one to the other, which helps us realize one as the reparameterization of the other. Let me next define the notion of concatenation. We have already seen that as well, but let me define it a bit differently here. We will not insist that the domains are domains of definition of the curve is 0, 1 here. So, we will rather play around with the domain where our curve is and attach it. It will be clear when I define it. So, we say let gamma 1 from A1 B1 to C and gamma 2 from A2 B2 to C be two curves such that the terminal point of gamma 1 and the initial point of gamma 2 coincide. The terminal point of gamma 1 coincides with the initial point of gamma 2. So, the image is going to be something like this. So, gamma 1, which I am going to draw with say purple, will be a point say from Z1 to Z2, and the curve in red might be the curve gamma 2 which starts at Z2. Remember that the terminal point is the image, so that is going to be Z2, image of B1 under gamma 1, and the initial point of gamma 2 is going to be the image of A2 under gamma 2. So, this is going to be the point and this is how it should look. But we would like to now define the concatenation of gamma 1 and gamma 2. Let us do that. To do that, let's do a reparameterization of gamma 2. Let gamma 2 tilde be reparameterization of gamma 2 by through the homeomorphism phi, which is given from A2 B2 to B1. It's just a translation, by the way. It's just a translation, and the translation is done by looking at B1 minus A2. The translation, the map is just t going to t plus B1 minus A2. If you notice that since A2 to B1 and B2 to B2 plus B1 minus A2, and gamma 2, that means gamma 2 tilde of t is just equal to gamma 1. Okay, gamma 2, where is gamma 2 tilde defined on? Gamma 2 tilde is defined on B1 comma B2 plus B1 minus A2 into C, given by gamma 2 tilde of t is equal to gamma 2 of phi of t, that means gamma 2 of t minus, this is the map. Phi of t is the map given by t minus B1 minus A2. So you look at this particular reparameterization of the map gamma 2 tilde, this is up to equivalence, right? Let us now define the concatenation of gamma 1 and gamma 2 in the following manner. Define, I will just write gamma 1 plus gamma 2 instead of gamma 1 dot gamma 2. Let me use this notation, gamma 1 plus gamma 2. Where is this defined on? This is defined on A1 and B2 plus B1 minus A2. This is the domain of definition of gamma 1 plus gamma 2 defined by gamma 1 plus gamma 2 of t is given by gamma 1 of t when t is between A1 and B1, and it's going to be given by gamma 2 tilde of t when t is between B1 and B2 plus B1 minus A2. So the first exercise, so this is you look at the figure, it is just the curve which starts at Z1 goes till B1 to Z2, and after B1 it goes along the red curve to Z3. So that's precisely what the concatenation is doing geometry. Immediate exercises for you would be to show that even though we defined it in this manner, gamma 1 plus gamma 2 is a continuous map. So it is indeed a curve. So this is the first exercise. The second exercise would be that if you are concatenating more than two curves, then the order in which the associativity is preserved. So if you first concatenate gamma 1 and gamma 2 and then you concatenate it to gamma 3. So the conditions of concatenation are preserved here. Let's assume that I did write it down explicitly. Basically the initial point of gamma 2 is the terminal point of gamma 1 and the initial point of gamma 3 is the terminal point of gamma 2. Then we can talk about concatenation of gamma 1 and gamma 2 and then concatenating it with gamma 3. We could also consider the concatenation first of gamma 2 and gamma 3 and then concatenating it with gamma 1, and what we get is finally the same. In fact, it's the same map. It's not up to equivalence that we are talking about. This is going to be the exact same curve that we are going to obtain. Okay. Let me now prove a proposition which tells us that concatenation and reversal are defined well up to equivalence. So let's write it down. Proposition that gamma 1, gamma 2, gamma 1 tilde and gamma 2 tilde be curves such that the initial point of gamma 1 is the, or gamma 2 is the terminal point of gamma 1, coincides with the terminal point of gamma 1. Further, let gamma 1 tilde and gamma 2 tilde be reparameterizations of, continuous reparameterizations of gamma 1 and gamma 2 respectively. Let gamma 1 tilde and gamma 2 tilde be continuous reparameterizations of gamma 1 and gamma 2 respectively. So, in particular, the initial point of gamma 2 tilde, which is the same as the initial point of gamma 2, coincides with the terminal point of gamma 1 tilde. Remember that after reparameterization, the image and the initial point and the terminal point are fixed. So, we can indeed talk about the concatenation of gamma 1 tilde and gamma 2 tilde as well. What is the proposition telling us? I can write down the statement. Then gamma 1 plus gamma 2 is equivalent to gamma 1 tilde plus gamma 2 tilde. Further, minus of gamma 1 is equivalent to minus of gamma 1 tilde. These are operations which preserve the equivalence class. Let's give a quick proof of the proposition. Let me not give you complete details. Let me just indicate the proof for you. Gamma 1, let's say that it is defined on A1, B1 into C, and gamma 2 be defined on A2, B2 into C. And our gamma 1 plus gamma 2 is clear. Suppose gamma 1 tilde is defined on C1, D1 to C, and gamma 2 tilde is defined on C2, D2 to C. So, there are many parameterizations which we will have to deal with. Let me define what is the reparameterization. So, gamma 1 plus gamma 2 is a map from A1 to B2 plus B1 minus A2, and gamma 1 tilde plus gamma 2 tilde is a map from C1 plus D2 plus D1 minus C2 into C. So, the goal is to obtain a reparameterization of gamma 1 plus gamma 2 into gamma 1 tilde plus gamma 2 tilde. Let me just tell you that it's obtained by the reparameterizations which are already there here. There is a phi 1 here and there is a phi 2 here, because these are already reparameterizations, isn't it? So, let me just define what the reparameterization psi is going to be from A1 B2 plus B1 minus A2 into C1 D2 plus D1 minus C2, and leave the rest to you. So, let us define psi from A1 B2 plus B1 minus A2 to C1 D2 plus D1 minus C2 in the following manner. We will define psi of t. This is going to be just phi 1 of t when t is in the interval A1 less than or equal to t less than or equal to B1. Now, it's in the second part that we will have to worry about when it's less than, when it's from B1 to B2 plus B1 minus A2. The first thing we will do is we will translate it back to the old interval so that we can apply phi 2, and that's going to be t minus B1 plus A2. You notice at B1 this is phi 2 of A2, which is going to be C2. But now we are not done, we will have to translate it. Once we apply this, we will have to translate it. So, for translating, let me just rewrite this to the left a bit. This is going to be phi 2 of t minus B1 plus A2, and then we will translate it to the place where we have to worry about all these things. So, that is going to be plus D1 minus C2. So, let us see, at t equal to B1, this is going to be phi 1 of A2, which is C2, and the eventual value is going to be d1, which is correct, which is precisely what we want, because psi 1 of b1 is equal to d1, so it ends at d1. So this is the perfect map that we have to worry about. Let me leave it as an exercise to check that psi, which is obtained by pasting phi1 and phi2 in the right manner, is a homeomorphism. And therefore, we have gamma 1 plus gamma 2 is obtained as a reparameterization of gamma 1 tilde plus gamma 2 tilde. Let's also look at gamma 1, and let's now look at gamma 1 minus of gamma 1, which is now defined from minus of b1 minus of a1 into c, and we would like to worry about what is minus of gamma 1 tilde, which is from minus of d1 minus of c1 into c. We already have a map phi from a1 b1 to d1 c1. I will just say that minus phi will be the map which will work here. Maybe I'll just leave that as an exercise for you. I have just given you what the hint would be and include the proposition. So basically we have proved that the operations of concatenation and reversal are well defined up to equivalence relation. So let me give you one more exercise. This exercise relates the notion of reversal and concatenation. So let's consider gamma 1 and gamma 2 to be two curves such that the initial point of gamma 2 is coinciding with the terminal point of gamma 1. And let's look at the reversal of this concatenated curve. This is going to be equivalent to minus of gamma 2 followed by minus of gamma 1. Okay, so we have defined what a curve is and we have seen many operations on curves, but we have only used the very basic notion of continuous curves till now, and we know that continuous curves can at times behave very arbitrarily, and it might not be very easy to do analysis if we focus on the entire collection of continuous curves at our disposal. Rather, what we would do is we would specialize and look at certain special curves which are called rectifiable curves. Let me just define what a rectifiable curve is. Before that, let me define what arc length of a given curve is. So, definition of arc length. Let gamma be a curve defined on the interval AB. We define be a curve. We define the arc length which is denoted by mod gamma, which is the arc. This is the arc length. This is defined to be the supremum over summation mod gamma of tj plus 1 minus gamma of tj, where j is going from 1 to n, and let's say where the supremum is being taken over. The supremum is over both n and all partitions t0 less than t1 less than, so I think maybe I should put a 0 here, t0 less than t1 up to tn, where t0 is our a and tn is the point b. So you look at the partition of AB into t0, t1, t2 up to tn. Look at the absolute value of the complex numbers gamma of tj plus 1 minus gamma of tj at each stage. Take the sum. And now let's look at the supremum over all such partitions. The supremum is what is called as the arc length of the curve gamma. Okay, and we say that a curve is rectifiable if the arc length is finite. Curve is rectifiable if the arc length is finite. But if you look at the definition, it's not a very accessible definition. It's not very easy to check whether a given curve is having finite arc length or not, because computing the arc length per se is not straightforward, at least from the definitions. So what we will do is we will try to get hold of a good condition with which we will be able to talk about the curve being rectifiable or not in an easier manner. And the right conditions or the easy condition to look at is when our given curve is continuously differentiable. We say that a curve gamma from AB to C is said to be continuously differentiable if the following limit exists. If gamma prime at t naught, which is defined to be the limit as t goes to t naught, where t belongs to a b minus the point t naught of gamma of t minus gamma of t naught by t minus t naught exists and is continuous. Now, the continuously differentiable curves are quite nice in the sense that it is very easy to compute the arc length of such curves. But before we actually give the right formula to compute the arc length of such a curve, let's just do a preparatory lemma. Let G from A, B to C be continuous. Then the absolute value of integral of g of t dt, this is less than or equal to the integral of the absolute value of g of t dt. Well, the integral is from a to b. So for real valued functions, integrable continuous functions g, this was a theorem which you would have seen in your real analysis course, but right now we are looking at complex valued functions. So it might be a good idea to give a proof of this statement before we venture into anything more. Before we go ahead, however, let me just, for the sake of clarity, let me just define the integral of g of t dt. This is just defined as the integral of the real part of g of t dt plus I times the integral of the imaginary part of g of t dt. So when I write integral of g of t dt, where g is a complex valued function, this is the definition. The right hand side is straightforward because mod g of t is anyway a real number. Okay, let's try to prove this statement. The proof is quite straightforward. So let's fix a point theta in R, and let's look at the real part of e to the power I theta times integral from a to b g of t dt. If you remember the characterization of absolute value in terms of the supremum of e to the power I theta times z, you would see that we are going in that direction. But before applying anything more, this is just going to be the integral of the real part of e to the power I theta g of t dt. And if we look at the absolute value, this is going to be the absolute value of this function. But from our real analysis course, the right hand side is the integral of a real valued function, and this is less than or equal to the integral of the absolute value of real part of e to the power I theta g of t dt. and we know that the real part is bounded by the absolute value of the function itself, and therefore this is going to be less than or equal to the integral of the absolute value of e to the power I theta g of t dt, which is equal to the integral of absolute value of g of t dt. We have that for each theta, the absolute value of real part of e to the power I theta integral a to b g of t dt is less than or equal to the integral of mod g of t dt. Now, by taking supremum, the inequality is preserved for this, because this is preserved for each theta, we get absolute value of integral of g of t dt is less than or equal to the integral of mod g of t dt. So, we have proved the analogous result when we look at complex valued functions. Alright, let me now give you the statement of the arc length for a continuously differentiable function. We will first show that the class of continuously differentiable function is a subclass of rectifiable curves. Let me write down the theorem. Let gamma from AB to C be a continuously differentiable curve. Then gamma is rectifiable. Gamma is rectifiable. That means it has finite arc length, and further the arc length of gamma is given by integral a to b mod of gamma prime of t dt. So, this formula is called the arc length formula. Let us give a proof of this. One side is going to be easy. We will first show that the arc length is bounded above by the integral which is written on the right. And to do that, let us take some partition. Let a equal to t0 less than t1 less than up to tn equal to b be a partition of AB. And now let us use the fundamental theorem of calculus. Fundamental theorem of calculus applied to both the real and the imaginary part of gamma separately. We will be able to write the following using the fundamental theorem of calculus. Gamma of tj minus gamma of tj minus 1, this is equal to, remember that gamma is a differentiable function. So, this is going to be integral of gamma prime of t dt from tj to tj minus 1. And now, if we look at the absolute value here, this is going to be the absolute value here, and we just proved a lemma which told us that this is less than or equal to the integral of mod gamma prime t dt from tj minus 1 to tj here. Now, if we look at the sum where j is going from 0 to n, the right hand side is just going to be equal to integral a to b mod gamma prime t dt. So, we take any partition, we have the summation of the length of the arcs gamma tj minus gamma tj minus 1. If you look at the sum of that, that is always bounded by the integral on the right, and hence taking supremum over all partitions and n, we get the arc length is less than or equal to the integral of mod gamma prime t dt from a to b. So, the thing to note here is that gamma prime is a continuous function. Since gamma is assumed to be continuously differentiable, gamma prime is a continuous function, and closed interval AB is a compact set in R, and therefore the theorem which states that continuous functions on a compact set is bounded about tells us that the integral on the right is a finite number, which tells us that the arc length of our given curve is finite. From this, as a corollary, I just said the argument why we can conclude this: mod gamma is finite and the continuously differentiable curve is rectifiable. We are not done, we have only shown one side of the inequality. We would now like to show that the integral is less than or equal to gamma. To prove the inequality in the reverse direction, let us consider the following set. Let E be the set of all those points T in the closed interval AB such that the following condition is satisfied, such that gamma, when restricted to the interval a comma t prime, the arc length of this particular curve, this is greater than or equal to integral a to t prime of gamma prime of t minus epsilon times t prime minus a. This is satisfied for all t prime less than or equal to t. Suppose we consider this particular set. So let me just go over the set for you once again. This is the collection of all those points t in the interval AB, so that for all t prime less than or equal to t, this inequality is satisfied. If you notice, okay, given epsilon positive, so this is a set which depends on epsilon, given epsilon positive, E epsilon be this particular set. So this is the set which satisfies the condition that for all t prime less than or equal to t, the restriction of gamma to a comma t prime, and if you look at that particular arc length, that will be bounded below by integral a to t prime of mod gamma prime t dt minus epsilon times t prime minus a. Now, if you take epsilon converging to 0 and if you show that this is satisfied for all t in AB, then we are getting our reverse inclusion as well, reverse inequality as well. So, that is going to be the goal now. Our goal would be to show that for every epsilon, E epsilon is equal to the entire set AB. And in order to do that, we will just prove that E epsilon is both closed and open and invoke the fact that AB is a connected set. Let us first show that E epsilon is indeed a closed set, but before that, I don't know whether I gave you the exercise before. Let me just check up. Right, so let me now give you an exercise here which I should have given to you when I defined the arc length. The exercise tells us what we can tell about the arc length of the concatenation of two curves. Prove that the arc length of gamma 1 plus gamma 2 is exactly equal to the arc length of gamma 1 plus the arc length of gamma 2. I'll leave that as an exercise. It's not difficult. You have to be a little careful with taking the partitions. It's analogous to how you would have proven a similar result with Riemann integrals in your real analysis course. So I'll let you think about that exercise right now because I'm going to use that now. We would like to use the fact that if you look at concatenation of two curves, then the arc length of the concatenation is the sum of the arc lengths. Alright, so let us now get back to proving that E epsilon is both closed and open. So the first observation is that E epsilon is closed, which is easy to prove. Let Tn be a sequence converging to T. Let Tn in E epsilon be a sequence converging to T. Let me call it T naught rather. Our goal is to show that T naught is contained in epsilon. To do that, we would like to show that we want to show that the arc length of gamma AT is, or rather AT prime, is greater than or equal to the integral AT prime mod gamma prime T prime mod gamma prime T dt minus epsilon times T prime minus A for all T prime less than or equal to T naught. This is what we want to show. And let me immediately tell you that for T prime strictly less than T naught, this is satisfied because Tn is a sequence which converges to T naught. So, there will be some point, if T prime is fixed, T prime be a point less than T naught fixed, then there will be a Tn which lies to the right of T prime, which will be greater than T prime, and such that T prime belongs to E epsilon, and therefore by invoking the same condition for Tn, we will be able to conclude it for T prime less than T naught. We only need to bother about the situation when T prime is equal to T naught or at the point T naught. If a sequence is converging to T naught from the right, from points that are greater than T naught, again we are done. We don't need to do much in that scenario. So let's assume that Tn is a sequence which is converging from the left to T naught. Then the observation which I would like to make is that gamma restricted to A T naught will by the exercise I just gave you, it's going to be a monotonous function, increasing function. This is going to be greater than or equal to mod gamma restricted to Tn for all n. If Tn is converging to T naught from the left, from points less than T naught, then this is certainly satisfied. This is going to be less than or equal to the integral from A to Tn mod gamma prime T dt minus epsilon times Tn minus A. Now there is nothing to prove, we just have to use one variable real analysis to conclude that as n goes to infinity we have what we want, and hence T naught belongs to E epsilon. The proof of closed is complete because we have just shown that every limit point of E epsilon belongs to E epsilon. The more difficult, not difficult, the more demanding part is the proof of the fact that E epsilon is open. So let's prove that any point of E epsilon is an open set, is an interior point. So the claim now is to show that E epsilon is open. Let T naught be some point in E epsilon. We will show that there is a delta such that T minus delta to T plus delta is contained in E epsilon. We already know that T naught minus delta to T naught, this is contained in fact this is contained in, where delta is small enough, this is contained in E epsilon. Delta is small enough so that this interval is contained in the interval AT. We would like to show that there is a delta such that T to T plus delta is also contained in E epsilon. That is the goal. In order to do that, let's get back to the very definition of continuously differentiable. We know that gamma is continuously differentiable at T naught, and since gamma is continuously differentiable at T naught, we have absolute value of gamma given epsilon positive, there exists delta small enough such that mod of gamma of T minus gamma of T naught by T minus T naught minus gamma prime at T naught this is less than or equal to epsilon by 2 whenever mod of T minus T naught, or rather let me just throw away the mod and let me write this as this is less than delta. So let's assume delta is small enough so that T naught to T naught plus delta is contained in AB. So this is the epsilon delta definition of differentiability that is being used here. So after multiplying by T minus T naught and using triangle inequality, we will be able to write that mod of gamma of T minus maybe gamma prime T naught into T minus T naught minus mod of gamma of T minus gamma of T naught. This is less than or equal to epsilon by 2 times T minus T naught. And rewriting, we have mod of gamma of T minus gamma of T naught. This is greater than or equal to mod gamma prime at T naught times T minus T naught minus epsilon by 2 into T minus T naught. We also have that gamma prime is a continuous function as a function of T, because gamma is a continuously differentiable curve, and hence since gamma prime is continuous, we can pick delta small enough so that absolute value of gamma prime of T is less than or equal to absolute value of gamma prime at T naught plus epsilon by 2. So that for T in maybe T naught to T naught plus delta, we can say this. And let's now look at the integral from T naught to T of this, and the right hand side is going to be, it's a constant, so this is going to be less than or equal to the integral of this is going to be less than or equal to mod of gamma prime at T naught times T minus T naught. So this is going to be T naught to T minus T naught plus epsilon by 2 times T minus T naught. And by using the equality here, star, and this is star star, both these inequalities give what do we have? We have let me show you what star is so that I'll write it down accordingly. We get mod gamma prime T is, notice that it is less than or equal to here. So we have mod of gamma prime T dt. So this is dt from T to T naught. This is less than or equal to gamma prime T times T minus T naught, which is plus epsilon. This, however, tells us that this is less than or equal to this plus epsilon by 2. And let me just write that this is going to be gamma of T minus gamma of T naught plus 2 times epsilon by 2 is going to be epsilon into T minus T naught. Now from this, what we have is gamma restricted to T comma T naught. If you look at the restriction of gamma to T comma T naught and look at its arc length, that is going to be certainly greater than or equal to mod of gamma of T minus gamma of T naught. This is after all a very basic partition, right? In fact, there is no partition. T0 and T1 is the only point if you look at the partition there. So this is going to be supremum. So the arc length is going to be the supremum, and therefore this is going to be greater than or equal to this, which in particular is greater than or equal to mod of integral of T to T naught mod of gamma prime T dt minus epsilon times T minus T naught. Now by using the fact that T naught belongs to epsilon, let me just note that down, since T naught belongs to in E epsilon, the arc length of gamma restricted to A comma T naught, this is greater than or equal to integral A to, maybe I wrote it wrong here, this is T naught to T. This is going to be A to T naught mod gamma prime T dt minus epsilon times A minus T naught. And if we use these two equations now using star and star star, and the exercise of looking at the sum of the concatenation of gamma 1 and gamma 2 and the arc length being the sum of the arc lengths, we have integral gamma restricted to at is greater than or equal to integral a to t mod gamma prime t dt minus epsilon times t minus t naught. This is true for all t in t minus a. Yeah, I made a small mistake here. It's not a minus t naught, it is t naught minus a. Yeah, now it makes sense. This is going to be t minus a, right? So this is for all t in a to t naught plus delta. This means that t naught is an interior point. Therefore, E epsilon is open. And that means that it's both an open and a closed set, which implies that E epsilon is equal to the set AB. Because A is in E epsilon, it's non-empty, and therefore it has to be the entire set. Okay, good, because what we have just shown is that hence for all epsilon positive, integral or rather the arc length of gamma is greater than or equal to integral a to b mod gamma prime t dt minus epsilon times b minus a. But our choice of epsilon was arbitrary. This is true for all epsilon positive and b minus a is fixed. Hence, gamma has an arc length greater than or equal to mod gamma prime t dt. So, we have shown the inequalities in both sides, and therefore, mod gamma prime, the arc length of gamma is equal to the integral a to b mod gamma prime t dt as we had started out to prove. So, this makes the computation of arc length of continuously differentiable curves extremely easy. So, for example, if you look at the curve gamma z1 to z2, if you look at the arc length of this, now this is going to be, it's an exercise for you to just compute the integration rather, this is just going to be z2 minus z. And if you look at the arc length of gamma, where gamma of theta be equal to z0 plus r e to the power I theta for theta in 0 to 2 pi, this is just going to give you the arc length to be equal to 2 pi r. Okay, let me stop here.